Welcome back everyone to Math Explore Infinity. In our last video, we embarked on a mathematical journey through the Arzelà-Ascoli theorem, which unveiled the secrets of precompactness in subset of the space of continuous functions over a compact metric space. However, if we were to confine ourselves solely to this cultivated garden, the space of continuous function, this would be akin to experiencing only the blissful warmth of summer, where everything is in full bloom and each flower seems to reach its peak of beauty. But the mathematical universe is not just a single season, right? It's a year-round phenomenon. So to fully comprehend its complexities, we must also venture into the cool and intriguing terrain of winter. So in this mathematical landscape, much like the winter forest, right, we encounter functions that may not exhibit continuous summer-like smoothness. So instead, they are like snowflakes, right? Unique, intricate, and sometimes discontinuous. So this shift from the summer garden to the winter forest actually reflects our journey from the space of continuous function, right, into I would say the expansive realm of LP spaces, where we confront a broader spectrum of functions, right, each with its distinct characteristics. So we aim to actually mirror some of the fascinating properties we have uncovered in the summer garden, right, within the winter forest. So just as the Ascoli theorem eliminated conditions for precompactness in the space of continuous function, so what we seek to is to discover, we seek to discover similar guiding principles, right, that can navigate us through the wilderness of LP spaces. And this is actually where the Riesz-Kolmogorov theorem comes into play. So just as the Arzelà-Ascoli theorem did for us in the garden of continuous function, the Riesz-Kolmogorov theorem actually equip us with the knowledge and skills to navigate the mathematical winter forest effectively, right? Helping us to discern when the family of functions in LP exhibit strong compactness. So this lecture is mainly about the Riesz-Kolmogorov theorem and some of its profound consequences. So let's start, right, with some notation. So notation. Good. So this is just about we are going to define a shift function, right? A function evaluated at a translated point. So we set tau h f applied to x, right, to be the function f of x plus h, right? X is in Rn as well as h. Those are elements of Rn. Now let's state the famous Riesz-Kolmogorov theorem. So this will be theorem 4.26. So and this is, let me just write the name, Kolmogorov. Riesz Fréchet. Okay. Sorry. So let's call it fancy f, right? Be bounded subset be bounded be a bounded set in LP of Rn with P between 1 included and infinity. So let me just highlight where P lives. So F should be a bounded subset of LP. Now assume that let's say the limit of the norm of tau h f minus f, and this is h, of course. I'm sorry for my writing. So the limit when the norm of h goes to 0 of the LP norm of the difference between the shift function and the function itself equals to 0 uniformly in f, right? So if this holds, let me just recall what this means uniformly. So this means for every epsilon positive, there exists a delta positive, right? Such that the norm of tau h f minus f, the LP norm, strictly less than epsilon for every f in f, right? And for every h in Rn with norm of h strictly less than delta. So if this holds, then the closure of f, right, restricted to omega is actually I'm sorry. So if this holds, then the closure of f restricted to omega, I will just write f restricted to omega. So the closure of this, right, is compact for any measurable set omega, included into Rn, right, with finite measure with finite measure. So say the best measure of omega is finite. Okay. So the proof of this theorem actually is a bit lengthy and consists of 4 steps. So the proof is a bit constructive. It's really constructive. So in step 1, so we claim that so let's call it alpha 1. So we claim that let me use different color, that the norm of rho n, remember rho n was actually our sequence of modifiers, that the norm of rho n convoluted with the norm of rho n convoluted with f minus f, the LP norm of this, right, in Rn is actually less or equal than epsilon for every f in f and for every n strictly greater than 1 over delta, where the delta comes from the assumption that we saw in the Riesz-Kolmogorov theorem. This delta here. Okay. Then somehow I have to clear my throat every minute. I don't know why. So sorry for that. So this is our claim. So let's kind of prove why this holds. Let's see why this holds. So indeed, we have for every f in f, right? You have the absolute value of rho n convoluted with f, right? Applied to x minus f of x. This is just, let's go step by step. So this will be the integral over Rn, right? This is just the definition of the convolution product. F of x minus y dy. I will just write minus f of x down here in absolute value. So this is again equals to the absolute value of the integral over the whole domain Rn of f of x minus y minus f of x, right, times rho n of y dy. So remember, this is because remember that our sequence of modifiers actually integrate to 1 for every n. Okay, so now we can use triangle inequality. So this is also equal than the integral over Rn of the absolute value of f of x minus y minus f of x, right, times rho n of y dy. Of course, this is actually true because rho n is actually greater or equal than 0, right, for on the whole domain Rn. So now I'm going to do something here. So this is less or equal than, I'm going to write it this way, then so let me just write it first. Then the integral over Rn of the absolute value of f of x minus y minus f of y, minus f of x to the power p, right, times rho n of y dy, everything raised to the power 1 over p. And I claim that this actually follows from Hölder's inequality. This is Hölder's inequality. Well, how to see that? You just need to apply the Hölder's inequality to the following function, the function which at y associate the absolute value of f of x minus y, right, minus f of x, this to the power times rho n of y to the power 1 over p, right? So this element is actually in LP, and then you apply it with the function together with the function which at y associate rho n of y to the power 1 over p prime, where p prime is actually the conjugate exponent of p, right? So this is obviously an element of LP prime, right? LP prime, and remember that the modifying sequence actually integrate to 1. So the integral of rho n is 1, right, for every n. So this this follows from Hölder's inequality. Thus we obtain, right, if you actually raise both sides of the inequalities to the power p, and then you integrate both sides with respect to x, so we obtain that the integral over Rn of the absolute value of rho n convoluted with f applied to x minus f of x to the power p dx, right? This is actually less or equal than the integral over Rn, right, of the integral over Rn of the absolute value of f of x minus y minus f of x, this to the power p, right? Remember there was power p here, up, so times rho n to power y. Oops, I forgot the dy. Let me just shift this like this. So this times dx. Okay, now this is actually less or equal. I can pull out the rho n of y, right, out of the, I can change the order of integration, right, with the help of Fubini. So this is again the integral of rho n of y, right, of the integral over Rn, the absolute value of f of x minus y minus f of x, this is to the power p, dx, and then dy. But now remember that this quantity here is actually less or equal than epsilon to the power p, right, provided that the norm of y is actually strictly less than delta, right? This comes from the fact that this actually follows from the fact that, remember the assumption, we have that tau hf minus f, right, and the LP norm of this actually goes to 0 uniformly in f, right? So this was also as norm of h actually goes to 0. And also remember that I can even replace here the Rn, right, by, I wanted to write the support of rho n, but the rho n is actually supported into the ball centered at 0 and radius 1 over n. So this is actually less or equal than epsilon to the power p, right, provided that n is actually strictly greater than 1 over delta, right? Because let me tell you why. In fact, y is actually into this ball, right? This. So y actually varies. So here we are integrating. Y actually varies over the support of rho n, which is actually the ball of centered at 0 and radius 1 over n, right? Now, for this relation, for this quantity here to be less than epsilon to the power p, right, we know that the norm of y should be less than delta. But we know already that y is actually in this ball. So for the norm of y to be less than delta, so we need to have norm of y strictly less than delta, we need 1 over n to be strictly less than delta. And this actually means n is actually strictly greater than 1 over delta. So hence the norm of rho n convoluted with f minus f, the LP norm of this on Rn is actually less or equal than epsilon for every f in f, and for every n actually strictly greater than 1 over delta. Okay, good. So step 2. So in step 2, we claim that, we call it alpha 2. So we claim first that the norm of rho n convoluted with f, right? The L infinity norm of this in Rn, right, is actually less or equal than Cn, right? This is a constant which solely depends on n, right, times the norm of f, the LP norm of f, right, in Rn. Well, we are not going to prove this. I mean, this follows. I mean, this is actually easy to see. I mean, this follows by holders. I mean, you just have to write the full expression of the convolution product, right, of rho n with f. So this follows by Hölder's inequality. Right, with Cn being the LP prime norm. So let me just write the full expression, LP prime norm of rho n. So this is true, obviously. So we also claim, so this is, I mean, call it alpha 3, that the absolute value of rho n convoluted with f at x1, right, minus rho n convoluted with f at x2 at x2 is actually less or equal than Cn times the norm of f, I mean the LP norm of f, right, times the norm of x1 minus x2, and this holds for every f in the subset f, right, and for every x1, x2 in Rn. Again, where so let me just write it, where Cn, right, depends only on n. So to see this, observe that the gradient of the convolution product between rho n and f, right, is, I mean, we saw that we just need to shift the gradient to rho n, right? So this is this, right? And therefore you have that I mean the gradient of this convoluted with f, right? The n infinity norm of this, yeah, the n infinity norm of this in Rn, right, is actually, I mean, let's write everything step by step. So this is this, right, convoluted with f in L infinity of Rn, right, and this is by alpha 2, right? So by alpha 2, this is actually less or equals than the norm of the LP prime norm of this, right, in Rn times the norm of f, I mean the LP norm of f in Rn. So alpha 3 follows, right, with Cn equals the LP prime norm of the gradient of rho n. Okay, so step 2 was relatively easy. Yeah, so there was nothing to show. So step 3, so we claim that, I mean, given epsilon positive, right? So and omega a subset of Rn of finite measure we claim that there exists a bounded measurable subset of omega, right, such that alpha 4 holds, and this is the norm of f, the LP norm of f, right, LP of omega minus omega, right, this is small omega, so maybe I should write it somewhere here. There is a bounded measurable subset. Let's call it, let me just drag this to the right. Let's call it small omega, right, of omega, such that this is actually slightly less than epsilon for every f in f. So again, this is not difficult to see. I mean, indeed, we write, I mean, the norm of f in LP of omega minus omega. This is just triangle inequality, right? So this is less or equal than the norm of f minus Rn convoluted with f, right? This is in LP of omega minus omega, right? But you can even kind of bound it by the norm over the whole space Rn, right? Plus the norm of Rn convoluted with f in LP of omega minus omega. So, but observe that this is actually less or equal than epsilon, right? This was actually by I think it was alpha 1, right? And observe that this quantity here, this quantity here is actually, I mean, you can actually bound it by the norm of the L infinity norm of Rn in Rn. I mean, you can first of all bound it by this, right? But you can even bound it by the L infinity norm over the whole space, right? Times the Lebesgue measure of this. Let me just drag it. So this part is important. So times the Lebesgue measure of omega minus omega, right? So this raised to the power 1 over p. So in view, so maybe I use a stick with this color. So in view of alpha 2, I mean, it suffices to choose omega, right, such that the Lebesgue measure of omega minus omega is small enough. Right, because if this quantity is small enough, then I mean, kind of say this approaches 0, then you have that, then you will get that this whole quantity here, we get that this whole quantity here is kind of less than 2 epsilon or even epsilon if you want. So, okay, so step 3 is actually proof. So we move to the final step, which is the conclusion. So step 4. as I said, step 4 is about the conclusion. Okay, now observe that since LP of omega is complete, right? Is complete. It suffices to show that F restricted to omega, right, is totally bounded. Right, remember our black box, right, when we discussed the, I think, the Arzelà-Ascoli theorem, right, we saw that completeness plus, let me just write it, we saw that completeness plus totally bounded was equivalent to compactness. Of course, in a metric space. So this means, so let me just recall what totally bounded means. So this means given epsilon positive, right? So there is a finite covering of F restricted to omega, right, by balls of radius epsilon. Okay, so let's see how F restricted to omega is actually totally bounded. So given epsilon positive, right, so we fix a bounded measurable, we fix a bounded measurable set omega, right, such that alpha 4 hold. So let me just recall what alpha 4 was. So this means the norm of F, right, I mean the LP norm of this in omega minus omega, strictly less than epsilon. This is for every F in F, right? So also we fix n strictly greater than 1 over delta, right? And such that I think it was step 1, yeah, such that step 1 holds. So the family that we call calligraphic H, right, which are defined to be rho n convoluted with element of the subset F, right, but restricted to the closure of small omega. So the family H actually satisfies all the assumptions of the Arzelà Ascoli theorem. So I strongly invite you to watch the video on Arzelà Ascoli theorem if you haven't so far. So H actually satisfies all the assumption of the Arzelà Ascoli theorems. So I mean this is by step 2, right? So just to remind you of the assumption, bounded, H is bounded and equicontinuous. Boundedness on so you can actually check that if you want. Okay, so therefore H has compact closure, right? This is has compact closure, in the space of continuous function with compact over a compact metric space omega bar. So therefore, well, H has compact closure, right, in C omega bar, right, or W bar if you want. So consequently, well, just for your recall, omega bar is closed, right, and bounded in Rn, right, when it's compact, right, by Hahn-Borel. Hence compact. So you obviously have a subset of the space of continuous function over a compact metric space. So consequently, H also has compact closure in the space LP of omega. Therefore, hence we may we may cover H, right, by a finite number of balls of radius epsilon, right, in the space LP of omega. So say so H is actually contained, say, into the union of the ball centered at Gi and radius epsilon, right? I moving from 1 to, say, capital M, right, and function Gi are actually in LP of omega. Now consider the functions. Let's call it Gi bar. Those are just extension of the function Gi, right, to the space omega. So defined by say Gi bar is Gi, right, on omega and 0 on omega minus omega. Now we claim that the balls centered at Gi bar and radius 3 epsilon, right, in LP of omega actually covers f restricted to omega. So let me probably rewrite it. I'm sorry for, let me just write it as a claim. So claim f restricted to omega is actually contained into the union over I moving from 1 to m, right, of the ball centered at gi bar radius 3 epsilon. So let's see why. I mean, once we prove this, we are done. So indeed, given f in f, right, there is some I, I mean in 1m, right, such that the norm of rho n convoluted with f, right, minus gi, right, this is in LP of small omega, so actually strictly less than epsilon, right? I mean this, sorry. Good. So this actually follows from the fact that remember H is actually contained into this, right, moving from 1 to capital N. So now since the norm of f minus gi bar, right, in LP of omega, right, this is, let's raise it to the power p, right, so this is equal to the integral over omega minus omega bar minus omega of the absolute value of f to the power p, right, plus the integral over small omega of the absolute value of f minus gi to the power p. I mean, of course, this, I mean, those are just short notations, right? So don't be surprised if you don't see, I mean, dx or dy or whatever. Yeah. So this is equal to this, right? Because remember, gi bar was actually 0 on omega minus, I mean, omega minus small omega. So that is why we can actually split the integral of f minus gi bar over both domains. So we therefore have, by step 3, I think so. I think it was probably alpha 4, yes. So we have by step 3 that the norm of f minus gi, I mean the LP norm of this, or let's write it to the power p first, of omega, right, this is less or equal than the norm of f, right, in LP of omega minus omega, right, plus the norm of f minus di in LP of omega. Everything here raised to the power p. So this is actually, as I said, by step 3, this is less or equal than epsilon plus the norm of f minus gi in LP of omega. Oops. Everything to the power p. Because remember step 3 actually said that this is less than epsilon, right, for every f in f. So this means sorry. So this means that the norm of f minus gi in LP of omega, right, is actually less or equal than epsilon plus, I just remove the power. This is in LP of omega. Oops, I think this was actually small omega. Okay, so now we use triangle inequality. So this is less or equal than epsilon plus the norm of f minus rho n convoluted with f, right, in LP of small omega, right. I can even bound it by the LP norm over Rn, right, plus the norm of rho n convoluted with f minus gi, but now I have to keep the LP norm of omega. Now remember, this was actually strictly less than epsilon. This was actually by step 1, right? And this quantity also is actually strictly less than epsilon due to the fact that H is actually contained into to the ball centered at gi and radius epsilon I moving from 1 to n. So finally you have that this is less or equal than 3 times epsilon. So with this we get that let me just write first the result we obtain. So this means the norm of f minus gi bar in LP of omega strictly less than or equal than 3 epsilon. So this means that f restricted to omega, right, is totally bounded. It's totally, let me just write bounded here. Hence, f restricted to omega has compact closure in LP of omega. So, as I said, this ends the proof. Okay, good. Now, let's have a couple of remarks before moving to some corollaries of the Riesz-Kolmogorov theorem. So the first remark, good. When trying to establish that a family, say F, right, in LP of omega has compact closure, right, of course with omega bounded with finite measure. It is convenient, it is usually convenient to extend sorry, it's actually convenient to extend the functions to all Rn, right, then apply the Riesz-Kolmogorov theorem. I think this was theorem 4.26. and consider the restriction to omega. So the second remark is about it's about the fact that one cannot actually conclude, under the assumptions of Theorem 4.26, right? So let me just highlight that. This is the Riesz-Kolmogorov theorem. So we cannot, let me put it in color. So we cannot conclude that F itself has compact closure in LP of Rn. So we need an additional assumption. So an additional assumption is required. Right, and then we are going to describe this additional assumption in the following corollary. So this is corollary 4.27. So let call it F, right, be a bounded set in LP of Rn, right, with P between 1 and infinity. Let me just highlight bounded and P in this space. Now we assume that we still have our the assumption of the initial assumption of the Riesz-Kolmogorov theorem. So that is the limit of norm of tau hf minus f, right, the LP norm of this, right, equals to 0. Right? This is when norm of h goes to 0. And of course, this should be, this should hold uniformly in F, right? And we also assume, this is actually the additional assumption that I was talking about. So we also assume that, let me hide it in color. So which color? So we also assume that for every epsilon positive, right, there exists omega, right, subset of Rn bounded, measurable, such that the norm of F, right, in LP of Rn minus omega is actually strictly less than epsilon for every F in F. So let's call this probably alpha 5. So under these assumptions, we conclude that F has compact closure in LP of Rn. And this is even kind of, the reverse is also true, right? So let's go into the proof. So proof. So given epsilon positive, right, we fix omega into Rn, right, bounded, measurable, bounded, unmeasurable, such that say alpha 5 volts, right, to keep it short. Now by the Riesz-Kolmogorov theorem, right, by theorem 4.26, we know that F restricted to omega, right, has compact closure in LP of omega. Hence, we may cover, put it here, F restricted to omega, right, with a finite number of balls, right, of radius epsilon, of course in LP of omega. So this means that we can write F restricted to omega is contained to the union of balls centered at di radius epsilon, say I moving from 1 to n, right? Now, sorry. So of course with gi being in LP of omega. Now, the trick is, is similar as before, right? You set gi bar of x, right, to be gi of x, right? If x is actually in omega, right, and 0 in omega, in Rn, or in omega complement. So just to be Rn minus omega, just to be clear. So it is clear, you can check that easily. So it is clear that F is covered by balls B gi bar 2 epsilon, right, in LP of Rn. So what I mean is that you can actually check that F is contained to the union of this ball, moving from 1 to n, right, of gi by and radius 2 epsilon. Okay, of course, this is obviously an element of LP of Rn, right, because we extended, this is just an extension of the function gi on LP of omega to the whole space. So with this we are done, right? So right, because this is totally bounded, and then we know that completeness plus totally bounded is equivalent to compactness. Okay, good. So now let's have a remark. I think I said it already, that the converse is true. So let me just write it down. So remark, the converse of corollary 4.27 is also true So therefore we have a complete characterization of compact set, right, in LP of Rn. So we conclude this lecture, right, with a useful application, right, of the Riesz-Kolmogorov theorem. So this is actually corollary 4.28. Yeah. So let capital G, right, be a fixed function in L1, right, in L1 of Rn. Let me just highlight one, and let, say, let's call it the set F, right, defined to be G convoluted with element of the set B, right, where B is calligraphic B, of course, is a bounded set in LP of Rn, right, with P between 1 and infinity. Then F restricted to omega, right, has compact closure in LP of omega, right, for any measurable right, I think it looks ugly, for any measurable set omega, right, with finite measure. Okay, good. So let's go into the proof, right? I think the proof is not difficult. So proof. So the proof is about just verifying the assumptions of the Riesz-Kolmogorov theorem. So clearly F is bounded, right? Because remember B was bounded. F is bounded in LP of Rn, right? Let me just write Y as B as a subset of LP of Rn is bounded. You can check that, right? Sorry. On the other hand, if you write F, right, to be G convoluted with U, right, you're taking an element in F, right, so with U in B, you have the norm of tau H F minus F. As I said, what we are doing is just we are just verifying the assumptions of Theorem 4.26, right, the Riesz-Kolmogorov theorem. So the LP norm of this is equal to, we are now using just of this minus G. Just need to write things fully, right? Nothing complicated here. And this is actually, well, observe that this quantity is actually in L1 and U is actually in LP, And now you can actually use Young's inequality, or you can use Young's inequality and see that this is actually less or equal than the LP norm of U, right, times the L1 norm of tau H G minus G L1 norm. This is just write it, Young's inequalities. I strongly invite you to watch my video on, I think it was on measure theory, right, and integration. Yeah, we talk about Young's inequality over there, so just go and watch it. So now U is actually belongs to the set B, and B is bounded, so this is probably less or equal than C, right, and the C times the norm of this minus this, right, because I mean I said this is actually less or equal than C, right, as the set B is bounded by assumption. And now we conclude with the help of a lemma that actually says that this quantity actually goes to 0. So we just write and we conclude, because with this all the properties, or all the assumptions of the Riesz-Kolmogorov theorem are verified, and then we can conclude that F respect to omega has compact closure in LP of omega. So, and we conclude with the help of the following lemma. Sorry, on the following lemma. So I think this will be the last lemma, or the last thing we do in this video. So lemma 4.3. So let G in LQ of Rn, right, with Q between 1 and infinity. So let me just highlight that. It's very important. Then the norm of tau H. Remember, tau H was actually the shift function we defined at the very beginning. So the norm of this, the LQ norm of this, actually goes to 0, right, as norm of H goes to 0. So let's go into the proof, right? I think the proof is not that complicated. So proof. So given epsilon positive, right, there exists, I'm sorry if I'm not writing, let G in LQ with Q between 1 and infinity. So I'm just starting right away, so you should actually assume that, I have all the assumption already, right, and then I want to prove the result. So given epsilon positive, there exists, this is actually by Theorem 4.12. We remind you of that theorem. So the theorem actually says that, that the space of continuous function, right, with compact support on Rn lies dense in LQ of Rn, right, with Q between 1 and infinity. So given epsilon positive, right, there exists by Theorem 4.12 a function that we call say G1, right, in CC of Rn, space of continuous function with compact support, such that the norm of G minus G1, the LQ norm of G is actually strictly less than epsilon. So we write, now it's only about triangle inequality. So the norm of this, of tau h g minus g, the LQ norm of this is actually less or equal than the LQ norm of tau h g minus tau h g1, right? LQ norm of this plus the norm of tau h g1 minus g1, LQ norm of course, plus finally the norm of g1 minus g, LQ norm. But of course we saw that, I mean, this was actually slightly less than epsilon, and this is also slightly less than epsilon. So because I mean tau hg is just, I mean, the shift function, right? The function evaluated at a translated point, right? So this should also be less than epsilon, right? Because of this, of course. Okay, so this is actually less or equal than 2 epsilon, right? Plus the norm of tau hg. Let me write it. Tau hg 1, yeah, minus g1, the LQ norm of this. And of course, this actually goes to 0 as norm of h actually goes to 0. You can actually check that, right? And remember, g1 is actually continuous and has compact support, so somehow you can actually pull the limit inside the integral, and yeah. So hence, the limit, right, when norm of h goes to 0 of the norm of tau h g minus g, the LQ norm of this is less or equal than 2 epsilon. Of course, this is for every epsilon positive. So with this we are done, right? So this is basically where the proof ends, and yeah. So thank you very much for joining, for watching this video. Yeah, it was actually really fascinating and instructive, right? So thank you for watching, and see you in the next video, where we will talk about probably Hilbert spaces, right? And yeah, see you, bye.